Good day, Professor Van here. This video discusses transmission line parameters. We'll be discussing 8 transmission line parameters. First, we have the velocity factor. Next, we have electrical length. Third, input impedance. Fourth, reflection and reflection coefficient. The next will be standing waves, return loss, transmission loss, and transmitted power. First, let's take a look at how an electromagnetic wave behaves. An EM wave travels at the speed of light in a vacuum and slows down as its medium gets denser. As you can see in the animation below, light travels significantly faster in open space or in a vacuum compared when it is traveling through a medium and bouncing from atom to atom. Velocity factor. Velocity factor is the ratio of the actual velocity of propagation of the EM wave through a given medium to the velocity of propagation through a vacuum. It is given by the formula V sub f is equal to V sub b divided by c, wherein V sub f is the velocity factor, V sub b is the actual velocity of propagation, and c is our velocity of propagation through a vacuum, which is equal to the speed of light 3 times 10 raised to the 8 meters per second. The velocity factor at which the EM wave travels through a transmission line depends on the dielectric constant of the insulating material separating the two conductors. So this is another formula for velocity factor. It's V sub f equals 1 divided by the square root of epsilon r, wherein epsilon sub r is the dielectric constant of the material. Velocity of propagation. The velocity of propagation is the velocity at which the electromagnetic wave propagates along a transmission line, and this varies with the inductance and capacitance of the cable. So we have the formula T is equal to the square root of L times C. And then V sub B is equals to distance over time. If D is normalized to 1 meter, V sub B is equal to 1 divided by square root of LC, wherein V sub b is the velocity of propagation, L is the inductance per unit length, and C is the capacitance per unit length. Take note of the units. Next, let's discuss electrical length. Electrical length. Electrical length is different from physical length. Physical length is the actual length dimension of the cable. It is independent of the wave that is traveling through the transmission cable. Electrical length, on the other hand, is relative to the length of the wave propagating down the line. It is given by the formula beta L degrees equals 360 degrees times L divided by lambda. Or in terms of radian, we have beta L rad equals omega L divided by lambda, wherein beta L degrees is the electrical length in degrees, beta L rad is the electrical length in radians, L is the physical length of the transmission line in meters, and lambda is the operating wavelength in meters. Take note that we have to be consistent when using the units. Next, we have input impedance. For a lossy transmission line, the input impedance is given by the formula Z sub in equals Z sub O times Z sub L plus Z sub O times the hyperbolic tangent of gamma times L divided by Z sub O plus Z sub L times the hyperbolic tangent of gamma times L. Wherein Z sub in is the input impedance at a distance L from the load. Z sub L is the load impedance, Z sub O is the characteristic impedance, Gamma is the propagation constant, and L is the distance from the load. Now this is the formula for a lossless transmission line. It is given by Z sub n equals Z sub O times Z sub L plus J, this is the imaginary part, Z sub O times tangent beta times L divided by Z sub O plus Z sub L times tangent beta times L. And we have the same variables. The difference is we no longer have the propagation constant gamma, but in the place of gamma we have beta, which is the phase shift constant. For transmission lines terminated in a short circuit, the nature of the line will depend upon the physical length of the transmission line in relation with the wavelength that is propagating through the line. If the length of a short-circuited transmission line is equal to 1/4 the wavelength of the electromagnetic wave propagating through the line, the input impedance of such a line is maximum resistive. If it is less than 1/4 of the wavelength, it will have an inductive nature, and if the transmission line is more than 1/4 the wavelength, it will have a capacitive nature. The nature of the line will change if the transmission line is terminated by an open circuit. If the transmission line is terminated by an open circuit and the length of the line is equal to 1/4 the wavelength of the wave propagating through the line, then the input impedance will be at minimum resistive. But if it is less than 1/4 the wavelength of the wave propagating through the line, the input impedance will have a capacitive nature. Lastly, if the length of an open circuit transmission line is more than 1/4 the wavelength of the electromagnetic wave propagating through the line, then the input impedance will have an inductive nature. Next, let's proceed to reflection and reflection coefficient. When an electromagnetic wave travels down a transmission line, there are three possibilities. First, all the incident power is absorbed by the load. This happens when it is a matched line, or the load impedance is equal to the characteristic impedance of the line. This is called a non-resonant line or a flat line. The second possibility is all the incident power is reflected back to the source. This is a complete mismatch. This happens when the load impedance is equal to 0 or infinity, or load impedance is purely reactive. This is called a resonant line. The third possibility is that a portion of the incident power is absorbed by the load and a portion is reflected back. This happens when the load impedance is complex, or the load impedance is not equal to the characteristic impedance of the line. This is also called a resonant line. Reflection. A transmission line phenomena wherein a portion of the incident energy is delivered back to the source due to impedance mismatch. So in the image, we have our source. This is the source of our electromagnetic wave that travels down the transmission line. The electromagnetic wave that travels from the source to the load is called the incident wave. When the transmission line and the load impedances are not matched, there will be reflected waves. So only a portion of the incident wave will be absorbed by the load and a portion will be reflected back. Or sometimes, if it is a complete mismatch, then all of the incident wave will be reflected back to the source. Reflection coefficient. Reflection coefficient is a parameter that describes how much of a wave is reflected by an impedance discontinuity in the transmission medium. It is equal to the ratio of the amplitude of the reflected wave to the incident wave. We have a few formulas for reflection coefficient. First, we have in terms of reflected and incident signal. This is the easiest. So we have the reflection coefficient is equal to V sub ref divided by V sub ins, wherein V sub ref refers to the reflected wave and V sub ins refers to the incident wave. So in terms of current, we have I sub ref divided by I sub ins, and it has a negative value. For the reflected power and incident power, we have reflection coefficient is equal to the square root of P sub ref divided by P sub ins. And lastly, in terms of load impedance and characteristic impedance, we have the reflection coefficient equals Z sub L minus Z sub O divided by Z sub L plus Z sub O. And of course, the reflection coefficient is a unitless quantity. Next, let's proceed to the standing wave. This is the animation of a standing wave, color-coded black, created by the superposition of a left traveling wave, colored blue, and the right traveling wave, colored red. A standing wave, also known as a stationary wave, is a wave which oscillates in time but the peak amplitude profile does not move in space. The peak amplitude of the wave oscillations at any point in space is constant with time, and the oscillations at different points throughout the wave are in phase. The locations at which the absolute value of the amplitude is minimum are called nodes, and the locations where the absolute value of the amplitude is maximum are called antinodes. Standing waves ratio. This is the ratio that represents the maximum voltage or current standing wave over the minimum voltage or current standing wave. This is the formula for standing wave ratio, or SWR. V sub ins plus V ref divided by V sub ins minus V ref. Or we can also express that in terms of current. We have I sub ins plus I sub ref divided by I sub ins minus I sub ref. And lastly, SWR is also related to the reflection coefficient. So we have the formula SWR equals 1 plus the absolute value of the reflection coefficient divided by 1 minus the absolute value of our reflection coefficient. With a little bit of algebra, we can also compute our reflection coefficient in terms of SWR. Hence, we have the formula reflection coefficient equals SWR minus 1 divided by SWR plus 1. For a lossless line terminated in a resistive impedance, the relationship between SWR and the load and line impedance is given by these equations. For the first one, in the case of our characteristic impedance greater than our resistive load, we have SWR is equal to Z sub O divided by R sub L. For the second case, we have our resistive load greater than the characteristic impedance of the line, and so the SWR is equal to R sub L divided by Z sub O. VSWR in terms of forward power and reflected power. So we have VSWR equals 1 plus the square root of the reflected power divided by the forward power divided by 1 minus the square root of the reflected power divided by the forward power. Please take note that VSWR and SWR can be used interchangeably. This animation shows the standing waves wherein the transmission line is terminated by a short circuit. As you can see, Z sub L equals 0 ohms. The transmission line itself has a characteristic impedance of 50 ohms. And then if you look at the voltage standing waves, we have minimum points and maximum points, same as with the current standing waves. The points at which the absolute maximum for voltage occurs when the current is at absolute minimum. And the points at which the voltage is at absolute minimum are the points at which the current is at absolute maximum. So the reflection coefficient in this case is -1. Remember, the formula for reflection coefficient is Z sub L minus Z sub O divided by Z sub L plus Z sub O. So we have 0 minus 50 is -50 divided by 0 plus 50. It's just equal to -1. Next, this is the animation for the standing waves, wherein our load impedance is equal to infinity or an open circuit. So in this case, our reflection coefficient is equal to 1, and the same as before, the absolute maximum for the voltage occurs during the absolute minimum of the current, and vice versa. Next, in this case, we have our load impedance equals to 16.5 ohms, our characteristic impedance equal to 50 ohms still, and so we have a reflection coefficient equal to -0.5, and the voltage and the current standing waves still follows the same principle as before. In this example, we have our load impedance equal to 150 ohms and our characteristic impedance equal to 50 ohms. So this is still a purely resistive load, but in this case, our load is greater than the characteristic impedance of the line. So as you can see, the standing waves closely resembles the standing wave of ZL equals 16.5, but it has shifted. Now in this example, we have a load impedance of 10 plus J20 ohms. This is a complex number, so it is not only a purely resistive load, we have an inductive component in this case. Our characteristic impedance is still 50 ohms, so our reflection coefficient, remember the formula, Z sub L minus Z sub O divided by Z sub L plus Z sub O. So our reflection coefficient is equal to -0.5 plus J 0.5. Since the load impedance is a complex value, it is expected that our coefficient of reflection is also a complex value. For the last example, we still have a complex number as our load impedance, but in this case, it has a capacitive component. So we have our load impedance equal to 10 minus J20 ohms. The characteristic impedance of the line is still at 50 ohms. So our reflection coefficient is equal to -0.5 minus J 0.5. Next, let's take a look at return loss. Return loss. Return loss is the ratio of the power in the reflected wave to that in the incident wave. So by formula, we have 1 divided by our reflection coefficient squared. We can also express return loss in decibels. So we have RL sub dB equals -20 log of our reflection coefficient. Notice that we have a negative sign when expressing it in decibel. This is because it is a power loss, not a power gain. And then let's take a look at the transmission loss. Transmission loss, in terms of SWR, we have the formula TL sub dB is equal to negative 10 log of 1 minus SWR minus 1 divided by SWR plus 1 squared. And then in terms of reflection coefficient, we have TL sub dB equals negative 10 log of 1 minus the reflection coefficient squared. Now again, we have our negative sign denoting that this is a loss, not a gain. Lastly, let's take a look at the transmitted power. Transmitted power. Transmitted power is the amount of power absorbed by the load, and it is the difference between the incident power and the reflected power. So by formula, we have the following. P sub T is equal to P sub I minus P sub R. Second, we have P sub T is equal to P sub I minus the reflection coefficient squared times P sub I. And the third, we have P sub T equals P sub I times the quantity of 1 minus the reflection coefficient squared. Obviously, P sub T is our transmitted power, P sub I is our incident power, and P sub R is our reflected power. Next time, let's take a look at sample problems involving transmission line parameters.